It's their first taste of freedom. Researchers are releasing several Przewalski horses into the wild.
China released a group of wild horses into a desert where almost nothing was expected to change quickly. The plan was simple on paper: place them inside Kalamali, watch them survive, and measure the land over time. But after 3 years, the data coming back from the desert did not look ordinary. The change was not random, and it did not appear everywhere. It followed something moving through the sand. So what did those horses do to a dying desert that no human plan had managed to do before? Kalamali Ungulate Nature Reserve in northeastern Xinjiang was the desert at the center of this experiment. It covered 18,000 square kilometers of desert steppe, where winter could fall to minus 40 degrees Celsius and summer could rise to 40 degrees Celsius. Rainfall averaged only 150 to 250 millimeters a year, and before the horses arrived, the land was already classified as arid to semi-arid. Decades of human pressure had pushed the reserve into a quiet collapse. Mining operations, road construction, and illegal hunting had weakened the living system piece by piece. Ecologists call this defaunation, when large animals disappear from a landscape and the jobs they once performed disappear with them. The desert was not just empty. It was losing the forces that had shaped it for thousands of years. Mongolian gazelle, goitered gazelle, and wild-ass populations had all fallen sharply. These were the reserve's main large herbivores, the animals that kept movement, grazing, and pressure inside the ecosystem. On paper, Kalamali was still protected. In reality, its biological structure was slipping away because a protected boundary could not replace the animals that had vanished. Seeds were no longer spreading across the open ground the way they once had. Hooves were no longer breaking and aerating the soil. Vegetation kept thinning, and soil protection work alone could not reverse it. The damage was not only what people had done, the deeper problem was what the missing animals were no longer doing. China's State Forestry Administration faced a difficult truth. Protecting land could stop some pressure, but it could not restart the natural processes that only living animals create. Kalamali needed more than fences, laws, and reserve status. It needed a force that could move through the desert and make the land function again. The decision to bring back that force was not made lightly. The animal chosen had not lived in the wild anywhere on Earth for 32 years. Przewalski's horse, or Equus ferus przewalski, was not just another horse released into the desert. It is the world's last truly wild horse, genetically separate from domestic breeds, with 66 chromosomes instead of the domestic horse's 64. Its behavior had never been shaped by human domestication, which made this species different from every farm horse, riding horse, or feral horse on Earth. Dzungarian Gobi in Mongolia was where the last confirmed wild individual was seen in 1969. After that, the species disappeared from the wild completely. It survived only inside zoos and captive breeding centers in Europe, far from the open landscape it had occupied for tens of thousands of years. The animal still existed, but its world had been taken away. China began trying to reverse that loss in 1985, when it established the Xinjiang Wild Horse Breeding Research Center in Urumqi. The program imported 11 horses from European zoos and began breeding them with one goal in mind. This was not meant to be a display project. It was preparation for a return to the wild. Kalamali mattered because it sat inside the horse's historical range. Releasing them there was not placing an animal into a strange environment. It was sending an extinct species back into ancestral territory. The real question was whether decades of captivity had weakened the instincts needed to survive heat, cold, predators, scarce water, and open desert steppe. Early 2000s population growth finally made reintroduction possible, and in 2001 the first horses entered Kalamali. They walked into a desert that had been without them for longer than many researchers had been alive. The release was not just a conservation step. It was a test of whether a lost wild animal could still remember how to belong. The horses survived, and within 3 years the monitoring data from Kalamali began showing changes the original models had not fully predicted. Ecological monitoring in Kalamili did not rely on guesswork. Researchers used NDVI, or Normalized Difference Vegetation Index, a satellite method that measures vegetation density and green cover across the entire reserve. It works by comparing reflected light wavelengths from plants over time. This gave scientists a before and after view of the desert, not from one small plot, but across the full landscape. NDV. Eye comparisons between the pre-reintroduction period and years 3 to 5 after the horses were released showed a clear change. Vegetation cover increased in areas where the horses were known to range. The pattern did not simply follow hills, valleys, or water points. It followed the movement of the horses, which made the recovery harder to explain as ordinary protection alone. Control areas inside the reserve made the finding more important. These zones had the same protection from human pressure, but they did not have regular horse presence. During the same period, vegetation returned much more slowly there. This gave researchers the direct comparison they needed. If protection was equal but recovery was faster where horses moved, then the horses became the most likely active force. Ground-based vegetation transects confirmed what the satellite images were showing from above. In horse-grazed areas, plant species composition began moving back toward the steppe grassland structure of healthy Kalamili habitat. Ungrazed areas stayed closer to the old damaged baseline with thinner growth and lower diversity. The desert was not just becoming greener, its plant community was beginning to organize differently. Rate of recovery became the detail that surprised scientists most. The original ecological models had predicted gradual improvement, even under optimistic conditions. But the monitoring data showed faster change across a wider space than those models had captured. The horses were not simply surviving in Kalamili. Their presence was helping restart patterns the desert had been missing. The satellite data showed that something real was happening. Explaining it meant looking at the ground itself, where the horses were doing something no human conservation tool could fully copy. Przewalski's horses changed Kalamili first by moving seeds through the desert. A single horse produces about 15 to 20 kilograms of dung each day, and each kilogram can carry hundreds of undigested seeds from the grasses and forbs it has eaten. A herd of 50 horses becomes a moving seed system, spreading future plants across open ground where that natural network had been missing for decades. Horse hooves did something the desert soil badly needed. Unlike the split hooves of goats or sheep, their steps pressed into compacted ground and created small channels in the soil. Those channels helped water sink in and gave seeds a better chance to take hold. In a damaged desert, no simple soil treatment or plant-based repair could copy that constant physical action. Wild horse movement also made their impact different from livestock. Przewalski's horses live in tight family bands and cover territories of more than 200 square kilometers. They keep moving instead of staying in one small area. That matters because livestock often concentrate around fixed spots, and that pressure can strip fragile desert plants. The horses spread their grazing across space. Kalamili's data exposed the mistake in earlier models. Some predictions had been built partly on livestock impact research, but Przewalski's horses were not behaving like managed animals. They had a wild behavioral ecology. Their grazing, movement, and seed spreading worked across the landscape in a way the models had not fully expected. Soil analysis made the change even clearer. Horse-grazed areas showed improvements in aeration, organic content, seed bank density, and water retention. These were deeper signs than green cover alone. Vegetation can rise and fall with weather, but improved soil structure lasts longer. The horses were not only feeding on the desert, they were helping rebuild the ground beneath it. The horses were moving seeds, opening the soil and reshaping vegetation. But the next surprise was that their effect reached animals they never touched at all. Wild ass populations in Kalamili were already declining before the horses returned. Equus hemionus, along with other large herbivores, had lost ground as human pressure reshaped the reserve. The strange part was that Wild Ass and Przewalski's horses had evolved in the same landscape for tens of thousands of years, but modern damage had separated them. One species had declined, the other had disappeared completely. Horse reintroduction changed more than the plants the animals grazed. As vegetation recovered in horse-used areas, wild ass numbers in the reserve began rising as well. This mattered because protection alone had not produced the same recovery. The evidence suggested a co-evolutionary link. By rebuilding vegetation structure, the horses were creating conditions that helped another ancient desert species return. Ecologists call this a trophic cascade, when one returning species causes changes across several levels of an ecosystem. The horses were not hunting wild ass, they were not directly managing birds, insects, or plant communities. But by restoring seed movement, grazing patterns, and soil function, they restarted processes that many other species depended on without ever touching them directly. Yellowstone offers the clearest comparison. When wolves returned in 1995, they changed elk grazing behavior, which allowed riverside plants to recover, which stabilized riverbanks, which even affected river movement. Kalamili showed a desert version of the same idea. The driver was not a predator. It was a wild grazing animal moving through the land in a way livestock models had not predicted. Kalamili field surveys began showing the wider biological shift. Plant species composition changed in horse-grazed areas, bird presence shifted, and insect populations followed the recovery of vegetation. These changes extended beyond simple green cover. The reserve was not only growing more plants, its biological structure was beginning to reconnect. The cascade was the result that pushed the science beyond the original models, but it also raised a harder question: how much of the recovery came from the horses, and how much came from the reserve's other conservation measures? Kalamili's recovery did not happen under one single change. The reserve introduced horses during the same period that human activity was reduced, anti-poaching enforcement increased, and mining restrictions became stronger. Each measure could have helped the ecosystem. That is why the results were powerful but also difficult to separate. The horses were part of a larger conservation program, not an isolated experiment. NDVI spatial analysis gave researchers the clearest horse-specific signal. Vegetation recovery matched the areas where the horses regularly moved more closely than it matched protected zones alone. Areas with the same level of protection but without regular horse presence recovered more slowly. That difference mattered because it showed protection helped, but horse movement seemed to add something active. Soil analysis gave the second clue. Horse-grazed areas showed changes in aeration, organic content, and seed bank density. These are not changes that fences or patrols create by themselves. They match the physical work of horse behavior: hooves opening compacted soil and dung carrying seeds and nutrients. Control areas with reduced human pressure did not show the same pattern. Methodology still could not answer every part of the question. Researchers could see that the horses were linked to faster recovery, but they could not fully prove whether the same results would have happened without the wider protection program. The horses needed safer land to survive. The harder question was whether safer land alone could have restored the desert at the same speed. Available Kalamili data points to the horses as the active driver of ecosystem change. But the honest answer is more complex. Their biological effects worked inside a protected environment, and published research has not fully quantified how much recovery came from the horses versus reduced human pressure. That uncertainty does not weaken the result. It makes the science more honest. The horse effect was real, but measuring it was not simple. And the bigger complication was still ahead, because the program soon faced a question its designers had not expected when the first horses entered Kalamili in 2001. Przewalski's horse recovery created the kind of problem conservation programs rarely reach. From the first release in 2001, the Kalamili population grew to more than 400 wild individuals by 2020. That was a clear success. The horses were surviving, breeding, and proving that the desert could support them at scale. But success also meant the reserve now had to ask how many horses the land could safely carry. Kalamili Nature Reserve covers 18,000 square kilometers, But the horses do not use every part of it equally. Some areas have better forage, better movement routes, and stronger seasonal value. Their ranging patterns naturally concentrate in the most productive zones, so even inside a huge reserve, the pressure from grazing, hooves, and repeated movement can build unevenly in the places the horses use most. Official carrying capacity for Przewalski's horses in Kalamyli has not been clearly determined and published. Monitoring reports show population growth as a success, but they do not yet give one fixed number where the balance turns. That missing threshold matters because the same population increase that proves the program worked could become risky if the horses grow beyond what the landscape can renew. Moderate horse density helps the desert through mobile grazing, seed dispersal, and soil aeration, but high density can reverse those benefits. If grazing pressure becomes faster than vegetation recovery, the difference between wild horse impact and livestock damage begins to disappear. The same animals that rebuilt the system could start stressing it, not because they failed, but because they succeeded too well. Reserve managers and Xinjiang wildlife conservation programs are now watching population dynamics closely. The challenge is no longer just whether the horses can survive. They clearly can. The harder question is how to keep their numbers inside the range where their presence remains restorative instead of destructive. The carrying capacity question is now the unresolved management test, but it leads to an even larger mystery: whether the transformation seen in Kalamyli can ever be repeated in another desert. Mainstream ecologists see the Kalamyli recovery as the result of several actions working at the same time. The horses mattered, but so did reduced human activity, stronger anti-poaching enforcement, and habitat protection. In this view, giving the horses too much credit risks overstating their role, because the reserve was also removing the pressures that had damaged the desert in the first place. Horses' primary driver evidence comes from the NDVI maps and soil data. Protection can stop new damage, but it does not move seeds, open compacted soil, or reshape vegetation structure. The horses did all three. Recovery also followed horse ranging areas more closely than protected zones alone, which made their movement look like the active mechanism behind the change. Climate-based explanation is the most skeptical reading. It argues that changes in rainfall across Xinjiang during the reintroduction period may have helped vegetation recover, while the horses were simply present at the same time. But this explanation is weaker because the recovery pattern was not spread evenly across the reserve. It matched horse behavior more closely than broad precipitation patterns. Scientific disagreement is not about whether the horses helped. Both the mainstream view and the horse-driven view accept that Przewalski's horses produced real ecological effects. The disagreement is about weight. One side sees them as one factor among several. The other sees them as the biological force that turned protection into actual ecosystem recovery. Available published data supports the most balanced answer. The horses appear to be the active driver of ecosystem change, while protection created the safe conditions they needed to work. Without protection, the horses may not have survived. Without the horses, protection alone may not have restored the desert at the same speed or in the same pattern. The evidence points strongly toward the horses as the main biological force. But whether Kalamyli can become a model for other deserts is the question scientists are still careful not to answer too quickly. Przewalski's horses entered Kalamyli Nature Reserve in 2001 as a species that had been extinct in the wild for 32 years. They did more than survive. They bred, spread, and grew to more than 400 wild individuals, enough to leave a measurable mark on the desert. This mattered because a few animals can be symbolic, but a growing wild population can begin to change how a landscape works. Satellite NDVI data and ground surveys began showing the first clear signs within 3 to 5 years. Vegetation recovered faster in the areas where the horses ranged, and the change was larger than the program's models had expected. Researchers had predicted gradual improvement, even under hopeful conditions. Instead, the desert showed recovery at a speed and scale the models had not fully captured. Horse behavior explained why the change looked different from ordinary restoration. Their daily seed dispersal moved plant life across territories of more than 200 square kilometers. Their hooves opened compacted soil, and their grazing spread pressure instead of locking it into one place. These were living processes, not tools. No plant-based repair or soil treatment had produced the same effect in Kalamili during the earlier protection period. Wild ass recovery gave the result a wider meaning. As horse-used areas improved, wild ass numbers also began to rise, and field surveys recorded broader changes in plant diversity, bird presence, and insect populations. This confirmed the trophic cascade interpretation. The horses were not only changing the plants they ate, they were restoring functions that moved through the desert's biological structure. 3 years in Kalamili proved something specific and difficult to ignore. A wild herbivore, returned to its ancestral range with its natural behavior intact, can restart ecological processes that human protection can only make room for. Protection stopped further damage. The horses rebuilt movement, soil function, and vegetation structure faster than expected. Kalamili's data is now one of the most important arid rewilding records in the world. But scientists have been careful about one larger claim, because if it is true, it reaches far beyond one reserve in Xinjiang. Drylands cover about 40% of Earth's land surface, including arid, semi-arid, and dry subhumid regions. Across many of these places, desertification is getting worse because of climate change, overgrazing, and human development. So the Kalamili result matters far beyond one reserve. If large herbivores can help reverse damage in drylands, the question is not academic. It becomes one of the biggest ecological questions on the planet. Kalamili's success came from a very specific match between animal and place. Przewalski's horses were not strangers to that desert. They were returning to land their species had shaped for tens of thousands of years. Their movement, grazing, and survival behavior had been built by evolution for that environment. This is why scientists are careful. The same result may not happen if a different herbivore is placed in a desert outside its natural range. Global reintroduction programs give Kalamili more context, but not a perfect comparison. China's program is one of 3 major Przewalski's horse reintroductions, alongside Mongolia's Hustai Nuru and Great Gobi bee programs, as well as European efforts in Ukraine's Chernobyl exclusion zone and France. But Kalamili stands apart because it works at this scale in a mainly arid desert environment. Its dataset is unique, which also means it cannot yet prove a universal rule. Kalamili scientists have been clear about the line between evidence and overclaiming. Their data shows these horses, in this desert, caused ecosystem recovery faster than models expected. It does not create a simple formula for restoring every damaged desert. Each site has different animals, different history, different damage, and different protection efforts. That caution makes the results stronger because the science is not trying to say more than the data can support. Xinjiang's 1985 decision to bring in 11 captive horses from European zoos opened a question no one could fully see at the time. If the world's last wild horse, returned to the desert it once belonged to, could restart ecological work no human tool had copied, then what about other deserts? Maybe some damaged landscapes are not only missing water or protection, maybe they are missing the animal that once made them work. Kalamili did not prove one solution for every desert on Earth. It proved something more unsettling. Some landscapes may not heal until the species that shaped them finally returns.